Yes.
Yes. First of all, why is that light continuously shining? But okay. Okay, hello, I'm Romano, and I've been doing my bachelorette project at IDEMA, where I've been working on modeling bacterial colony growth using flexible bacteria. So now I'm gonna explain to you what I did the last 6 months in this project. So first I want to introduce you to bacterial biofilms. Meet my adorable friend here, E. coli. You have a usual E. coli that's just swimming about in its nutrient-rich water, and then it encounters a surface, for example a rock or a grain of sand, and then it collides with that. After this collision, a special substance is being produced called EPS, and that EPS works as a sticky gel, which first allows the bacterium to stick, and then when the bacterium is tightly stuck to the surface, it starts dividing, as bacteria usually do. And then you get a larger and larger structure, first staying two-dimensional and eventually growing into a large three-dimensional colony, which then, when the nutrients eventually run out, bursts open and releases free-swimming bacteria. These bacterial biofilms are commonly found, for example, as a cause of contamination on surgical implants like hip implants. Another way they are used is in water filtration. By letting bacterial water flow over bacterial biofilms, they are often cleaned. And another application is that they are often found in our teeth as dental plaque. So biofilms are a very commonly found structure. More than 90% of bacteria are, in fact, living in biofilms right now. So that shows that there's still a lot to investigate. Here we have a picture of a biofilm. The most people would just look at a biofilm like, okay, the rough shape, or perhaps how dense it is, or the shape of the bacteria inside. But our lab looks at it in a different way. We namely look at the lines that the bacteria form. As you see over here, those bacteria are well aligned. They lay parallel to each other and form a curve-like structure. This one forms sort of an S-like structure. These bacteria that lay in the same orientation or the same direction we call topological domains or orientational domains. If we then draw a line through all bacteria, you will result in these kind of lines, which are called director lines. And these director lines at least resemble, to me, somewhat of a human fingerprint. For example, this structure here, this straight line with a loop, is a really common pattern in human fingerprints. Another way we can characterize the internal order of a bacterial colony is by using defects. And for that I want to show you an example of that same colony. We're looking at this red point here, the red circle. So if we look at the blue lines would tell this point, okay, in order to be parallel with us, you have to be oriented from top to bottom. While the green lines would say, no, 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 no way, you have to be aligned from left to right. So, which orientation does this point actually have? Is it top to bottom or is it left to right? In mathematical sense, we call this point a defect because it has two orientations at the same time, which is in fact impossible. So we say that the orientation in this point is undefined, and therefore this point is a positive defect, we call this. At the same, for example, we have another point here in yellow, which is called a negative defect, where also the orientation is not well defined. So in order to model and investigate these topological domains and defects, one model I've worked with a lot is the model by Van Holte, who is also my supervisor in this project. And this is a resulting colony from one of his models. You can see that topological domains are forming. For example, the one I circle here in green. But compare them to the left side, and you can notice a few notable differences. What's one of the most common differences? Compare these, for example, this red one with a green one. What's the most noticeable difference?
Moet ik antwoord geven?
Ja.
Wat het grote verschil is tussen die twee?
What's one of the most noticeable differences between the red one and the green one?
Ja, de groen is kleiner.
Yeah, the size. The colonies are much shorter and much smaller. But also they are more distinct. Over here you can see that these domains are sort of merging or looping or doing all kind of beautiful patterns, which does not happen in the model by Van Holte. Another thing is that there are large amounts of defects while they are relatively scarce in the real life colony. And if you look at the edges, this one has really nice smooth edges but the model by Van Holte has all those outliers and pointy edges, and it's very rough. So my research goal was, can we improve this model by Van Holte in order to generate domains that are larger and are more continuous and result in something more similar to real life?
No.
And that will in fact be our conclusion. And after developing this system, we would also quantify it. The way we actually plan on making this possible is by allowing the bacteria to bend. If you look at the model by Van Holte, you could see that these bacteria are all straight. But if you look very closely, for example here, you can see that they have a curve in them. And this curving, we expect, plays a large role in making these smooth domains. And afterwards, after we develop this model, we want to quantify the behavior of the system and see if it actually resembles real life. So a quick recap of the model that Van Holte used. They model this beautiful E. coli a bit more simply than this. They say it's two circles with a spring in between. And by making this spring's rest length bigger and bigger, those two discs are pushed apart because the spring is literally pushing two of them apart. And eventually, after it's